Turn on the news right now, and you'll be bombarded with a specific kind of noise. A constant loop of terms like neural networks, teraflops, and machine learning makes it sound as if we've summoned a digital ghost. If you block out the anxiety about conscious machines and thinking monsters, you are left with something grounded and physical. It is a quiet metal box sitting on a desk. Opening that box reveals a sprawling neon-lit factory, a rigid landscape of geometric structures where the actual work happens. To understand artificial intelligence, we have to look past the hype of a thinking mind and map the physical architecture that processes the information. At the microscopic level, this environment operates as a vast digital grid of glowing paths and sharp geometry. This diagram shows the fundamental building block of that grid, the transistor. It is a microscopic switch that only understands two states. When the switch is up, it is illuminated, representing a yes. When it is down, it stays dark, representing a no. One switch is limited, but when millions of them are organized into precise rhythms, their collective flickering creates complex messages, images, and data. In a traditional computer, a central processing unit, or CPU, manages this entire grid like a general manager. Here, the CPU is executing a task. It is highly capable, but it operates through linear logic. It finishes one instruction completely before it can move on to the next. This linear process works for standard software, but it fails under the weight of artificial intelligence. When thousands of data points arrive at once, the single central node becomes a massive bottleneck. Traditional computing architecture was never designed to handle this volume of simultaneous data. Processing AI required a physical redesign of the entire system. To solve the bottleneck, designers traded the single intelligent manager for a massive specialized workforce. This is the Graphics Processing Unit, or GPU. It is the engine making modern AI possible, built from thousands of smaller processors working in unison. This diagram shows how the GPU handles a massive task. It divides the information into tiny individual pieces and solves every single one of them at the exact same time. This simultaneous processing, or parallel computing, allows the machine to recognize complex patterns instantly. It can identify a tennis ball in a photo because it processes every pixel of the image at once. This speed creates the illusion of a thinking machine. In reality, it is simply the physical capacity of specialized hardware to perform millions of tiny, synchronized calculations in a fraction of a second. However, these thousands of processors are useless without a constant, massive supply of raw data to keep them occupied. That data sits in permanent storage, a digital basement where information stays dormant until the system calls for it. To speed things up, the data moves from storage to the RAM, the system's workbench. This staging area holds the active information right next to the processors, so the GPU never has to wait. The data wakes up in storage, travels to the workbench, and is instantly consumed by the GPU nodes in a continuous physical cycle. Moving information at this scale has a physical cost. Toggling billions of switches every second requires a staggering amount of electrical energy. This energy creates intense heat. Industrial fans must spin constantly to prevent the entire physical architecture from destroying itself. Every AI model rests on this heavy, power-hungry industrial complex, vibrating with heat and electricity right on your desk. Leaving the neon paths of the architecture behind, we return to the real world and the quiet metal box. Without the buzzwords, the reality is clear. AI is a blazing fast calculator built of tiny physical switches. It is a tool, not a conscious entity. Despite its speed, the hardware is inert without us. It cannot assign itself a purpose or decide which data is worth processing. These millions of electronic functions have one practical goal: to handle tedious tasks in seconds, leaving us with more free time. A silicon chip can calculate millions of patterns in a heartbeat, but it has no sense of why it is doing so. The machine provides the efficiency, but the human decision to use that saved time to step away from the screen is the only part of the process that requires actual intelligence.